JP Chem. We are going to be talking about solubility today. And with solubility, it ties together our intermolecular forces with what we've been talking about lately and liquids. So we will be getting to talk about why certain liquids mix together and why certain liquids don't mix together. And it's actually kind of all based on their intermolecular forces. So we're going to start off a little bit by doing some reviewing of some terms that I'm confident that you remember from chemistry last year. But just in case, we're going to go over those first, and then we'll talk about how this ties together with what we've been doing lately. So a couple terms for things you may have forgotten. When we use the term solution, a solution is a homogeneous mixture. Homogeneous meaning it's the same, consistent from top to bottom. So it's identical in terms of its composition. If I took a sample from the top of the container or the bottom of the container, it would be identical if it's homogeneous. And a solution can be made with solids, liquids, or gases, and a combination of all of those. So just be aware of that. When we talk about the substance that's being dissolved, that is called the solute. And then the solvent is the dissolving medium for your solution. So it's the thing that's actually doing the dissolving. So when we get into talking about how things dissolve, you've probably heard of the phrase like dissolves like. And the general idea behind it is that substances are only going to dissolve in substances that are similar to it in its polarity. So what will end up happening is that polar solutes are only going to dissolve in polar solvents. Non-polar solvents will dissolve in non-polar solvents, and we haven't necessarily talked about them in a little while, but ionic solutes will also dissolve in polar because they both have kind of that they have that positive and negative charge things going on. But if I try to take an ionic solute, like let's say NaCl or something like that, that is not going to be able to dissolve in something that's non-polar, okay? What ends up happening is that the reason why this works is because when something dissolves in something else, there is an intermingling of the particles that has to happen. And for that to happen, there need to be similar intermolecular forces between the solute and the solvent. And that's because if you think about your solution, your solute and your solvent have to break apart and kind of make room in each other for the other one to come in. So if I have a solid solute, that needs to pull apart, and the other solvent particles need to work their way in. And what ends up happening is that the difference in the attractions needs to be pretty close to each other. So there needs to be very little difference in the attractions, because otherwise it's almost too much work to pull apart and go in there without the benefit to make that happen. And so we're going to kind of talk a little bit about the particle diagrams that go with that. And then you'll see this a little bit in the lab that we're going to run for chromatography. So if I take an ionic solute and I put it into a polar solvent, what ends up happening is that very structured ion lattice that we've talked about with ionic bonding, we talk about how those ionic bonds are very, very strong. What ends up happening is that when you put them into a polar solvent, and most of the time when we're talking about ionic solids, we're talking about water as our solvent. What ends up happening is that the water molecules surround the ions, and then what ends up happening is that the ion to dipole interaction, so the actual physical ion in the lattice and the waters that want to stick to that ion will compensate and actually be able to provide enough difference, or provide a good enough compensation so that the ion can be pulled off of there. It's called a hydration shell. So what happens is the water surrounds that, and when enough waters kind of surround that ion, then it dislodges it from the lattice and pulls it apart. And so that attraction is called an ion to dipole attraction. So this is kind of what it looks like here. So this is a block of NaCl here. Just as a reminder for you, the Na in this case is going to be the smaller one because of the periodic trends. It's an Na plus when it's in the lattice. And so the Na goes really kind of small because it's a positive ion, and the Cl is a minus ion, so it gets larger in size. And so when we talk about them, We identified the Na and the Cl, and you can kind of see here that these waters have surrounded these ions. And even though it's not drawn in the picture, there's water all around this little salt crystal. So there's water kind of swarming it. If you've ever seen like ants on like some ice cream that a little kid dropped, or maybe you dropped actually, they're swarming all over it. And so when there are enough waters that kind of swarm themselves around an ion, it breaks it out of the lattice. If you take a look at the picture here, the important part besides figuring out what the ions are and what their charge is going to be is orienting the water molecules in the correct way. So if you see here, this is the positive Na ion, and we have the negative end of the water, which is the O side of the water that's attracted to it. The negative chloride ions here have the H's turn towards them because the H's are partially positive, so they're going to be attracted to the partial or to the whole negative of the ion. So this is actually a kind of a test question that the College Board really likes to put on there. I've seen it on several exams, multiple choice and FRQ. And if they ask you to do that, there are things that you're going to need to know to draw into your pictures. You are going to have to correctly identify the particles and their charge. So in this case, they're trying to see if you know which particle is which based off your periodic trend, and then you know what type of ion they are going to become. They want to know if you can orient the water molecules correctly. So like I said, the H's are attracted to the negative ion because of the positive to negative attraction, and the same with the O's. And then you're going to want to have at least 4 waters surrounding each ion as well. So they'll surround to provide that hydration shell that we talked about. So this is something I've seen on the FRQ, and I've seen it on the multiple choice section. So just be aware of that. When you have a polar solute in a polar solvent, what ends up happening is that polar solutes that are solid are also in a lattice, but they are in what's called a molecular lattice. And so what that is it's just an organized structure, but instead of there being ions at the center of the structure, there are whole molecules. So like when I made that ice model for you and you saw all the waters in the rigid structure, the same thing happens in a polar solute as well. So what ends up happening is that the lattice that's holding that together, which by the way is far weaker than an ionic lattice, because a solid molecular lattice is just held together by intermolecular forces. So it's just the forces we've talked about that are holding our solids together. What ends up happening is that they fall apart, and then instead of breaking into ions like an ionic solute does, they break into just whole molecules, and then they have a whole molecule floating around. So what ends up happening though is that the polar solute in polar solvent, the dipole to dipole attractions are similar enough, and they can compensate for the breaking that has to happen when your solute and solvent make room for each other. And sometimes you're going to have hydrogen bonds happening when that happens as well. I kind of like this picture here. You don't necessarily need to maybe take a look at all the text here, but this is just generally showing what happens when ethanol, which is a type of alcohol, mixes with water. And I'll get the molecule on the next slide. So initially what's going to happen is that you are going to have the ethanol floating at the top of the water, and the ethanol is hydrogen bonded to itself and the water is hydrogen bonded to itself. But what ends up happening is eventually at this very interface where they mix, the water molecules will start to be able to form hydrogen bonds with the ethanol molecules, so they'll attract to each other, and then the solute and solvent will slowly start to intermingle, and those particles will be able to mix together. And it all happens because the intermolecular forces are similar enough that it's not this huge deal for me to pull apart each other and try and stick them in. So the forces that it takes to pull apart are roughly equal to the forces that will be formed when they come back together, and everything is right in the world. So this is the ethanol molecule, like I said, and water. So ethanol here has the ability to make a hydrogen bond at the end of its molecule with the O to H, and then the water would come into it and be attracted H from the water to the O of the ethanol and vice versa. So we'd have attractions in both of those places. Okay. When you take a polar solute and you mix it with a non-polar solvent, or vice versa, so I could take a non-polar solute and try and mix it with a solvent that's polar, what ends up happening is they will not mix together. So if you shake them up in a bottle, they would look like they were mixing, but eventually they would separate out into their own individual layers. What happens in that case is that the molecules that you have are just too dissimilar that the work it would take to pull it apart is not compensated by the new stuff that forms. This is an example of hexane, which I will show you a Lewis structure of in just a minute. Hexane is a 6-carbon long chain. It has just carbons and hydrogens, and so it's just a really big non-polar molecule. So what happens is if I take hexane and I mix it with water, it's going to lay out into these 2 distinct layers here. And carbon tetrachloride is actually another non-polar solvent or non-polar liquid. So you get these 3 layers if you mix all 3 of them together. But what ends up happening is that there are only London dispersion forces happening between the hexane molecule. And honestly, because they're big, they're actually pretty strong London forces. The hydrogen bonds that happen in the water are here. And so to break these London forces and break these hydrogen bonds, the hexanes have no place for the water to hydrogen bond. So the water never gets back the attraction that it would have to give up when it's connected to other waters. And so it's never going to really work because there isn't enough advantage for it to actually mix together. Okay. When you have a non-polar solute and a non-polar solvent, because it's just usually London dispersion forces that are in there, those are similar forces that when we break apart our solute and our solvent, we're breaking London dispersion forces, but when we bring them back together in a mix, we're making new attractions via the London dispersion forces. So generally, the effort going in is roughly equal to the effort going out, and you end up with that. So here is hexane that I talked about and water. And one of the experiments that they do sometimes is they will put elements, specifically they will put your halogens, iodine, they will put chlorine or bromine into a mixture of hexane and water. And what will happen is if you take elemental iodine and you dissolve it correctly or dissolve it completely, it will actually turn purple. Bromine turns brown and chlorine turns kind of a light green color. And the 2 possible solvents that you could have would be hexane and they would be water. So if you look at the Lewis structure for hexane here on the left, all you see is carbons and hydrogens, and that is non-polar. So that means that the only thing that this big molecule has here is London dispersion forces. On the right-hand side, we know water can make London dispersion forces, but it can also make hydrogen bonding and dipole to dipole. So when we think about iodine and what it's going to preferentially dissolve into, iodine is just 2 elements together, same elements. This is an incredibly non-polar bond. It's the least polar bond you could have. So it is going to preferentially mix with the hexane compared to the water. And this is actually kind of what you get here. It's kind of a cool looking experiment. So this bottom layer here for all of these is water. The top layer is hexane. And then you can see if they are dissolved, they will show a color. And if they are not dissolved, they will not show a color. So we've got kind of a purpley color here because the iodine dissolves in the hexane. It dissolves in the bromine. And then we've got chlorine here, just faintly dissolved in the hexane as well. But the water layer has basically nothing in it because they just don't want to mix together. So in all these cases, the halogens, the coming apart of the halogen and the coming apart of the water would not be enough benefit when they came back together to make that happen, but it can happen in the top layer. Okay, so hopefully that makes sense to you. You may see questions on the exam or a test or an understanding check asking about questions about this type of solubility. So just be prepared to answer them, okay? What we're going to be doing is we're going to be taking this into the chromatography process next, and then we will be doing a lab with that. So if you have any questions, make sure you ask. Otherwise, we'll be moving on to chromatography next. Good luck.